I would like to invite Professor Friedemann Reinhard from University of Rostock, and his talk is on positioning and readout for quantum magnetic field sensors. I'm sorry for the delay again, and please go ahead and start the talk. Thank you.
Okay, so good afternoon, everyone. Thank you very much, for inviting me to this event. I'm Friedemann Reinhard. I'm heading a lab at the University of Rostock in Germany. So this is northern Germany. The Vorlabs lab is, I think, in the south of Germany, where we are working on diamond magnetic field sensors. So in this talk, since it's an engineering conference that we have today, I would like to draw your attention to a few engineering challenges, which I think are important to solve to make progress in this field. But before we get to that, let me briefly introduce you to diamond sensors, what they are, what their promise is, and where they might find application. So what I personally find exciting about quantum sensing is that it bears some reminiscence to semiconductor technology. And I can best explain that by taking you to a work at my former place. So before coming to Rostock, I was heading a laboratory in Munich. And sometimes on the weekends, I would go to Germany's most famous science and technology museum, the Deutsche Museum, where they have many interesting exhibits, for example, on semiconductor technology. For example, one of them is an Apple I, a computer from 1967 with specs that were amazing at the time and a lot less impressive today. Now, what is interesting about that is if you are in this semiconductor department and you look at that, you may be impressed and you may be asking yourself the question, is this actually the oldest semiconductor device that they have on display? And it turns out that the answer is negative, because a few meters down the hallway, you will find this. This is a much simpler semiconductor device. It's just a single PN junction. It is a selenium photocell, in a way, a photodiode, which photographers used back in the day to measure the intensity of light before exposing the photograph. And the key point to note here is that this was a top-selling product already in the 1930s, long before, decades before materials were mastered on a scale that eventually allowed for the construction of large-scale computers. And it looks to me a little bit like history might be repeating itself. Again, we are at the dawn of a new technology. We call it quantum technology. We essentially believe that all the beautiful tools that emerged in our experimental labs in the past 5 decades certainly should find some applications in the real world. And it's natural to think that the killer application, again, as for semiconductors, will be a computer. And maybe this is indeed true. But maybe, again, we can have a faster road to the market and have applications on a shorter time scale if we also think about sensors. This is the agenda of my lab and many others. The qubit platform that we like most, that we like best for this work, is the nitrogen vacancy center in diamond. This is a color defect in diamond. You may recall from your chemistry classes that diamond is a carbon lattice, so it's transparent, but it actually is a lattice of carbon atoms, just as graphite. However, in reality, it's hardly ever a perfect lattice. Sometimes carbon atoms are replaced by nitrogen atoms. This is what we call a substitutional nitrogen defect. And sometimes carbon atoms are missing. This is what we call a vacancy. And sometimes these defects sit adjacent to each other, which we call the nitrogen vacancy NV color defect in diamond. It turns out this NV color defect is a true miracle of nature for several reasons. It is fluorescent, and the fluorescence is so bright that you probably could see a single defect with the naked eye. We've never tried that. We use electronics and cameras to do it, but it emits bright red fluorescence, and this is the basis of all our experiments. This is one of our diamond sensor chips, and all it takes us to operate this defect as a qubit is to bring it into a good fluorescence microscope. In a fluorescence microscope, we will see this. These red patches are regions where we locally doped the diamond with NV defects by ion implantation. So we locally converted the diamond into a red gemstone diamond. We can see this as red fluorescence, and zooming into the fringe region of one of these spots, we can eventually make up little clouds of light, each of them of diffraction limited size and of the same brightness. And in fact, each of these clouds is the light coming from a single nitrogen vacancy defect in diamond. So it is possible to see a single atom, essentially, a single nitrogen vacancy defect with a good microscope. Second important property, we can operate this defect as a qubit, and we can operate it as a magnetic field sensor. This is a very long story, which due to the limited time, I will cut in short. So the ground state, the electronic ground state of the nitrogen vacancy defect is a spin 1 triplet state. It's a stable electron spin with multiple sublevels. These sublevels differ in brightness, so we can optically read out the state of this electron spin qubit. Also, we can optically initialize it with a laser, and we can use it as a sensor because a magnetic field will enforce a Zeeman splitting onto these sublevels, because a spin 1 obviously is a paramagnetic system. This Zeeman splitting induced by a magnetic field can be measured by precision spectroscopy of the ground state microwave transition, which can be read out by fluorescence. And so each of these nitrogen vacancy defects, each of these nitrogen atoms frozen in the diamond, is a magnetic field sensor, which can be read out by spectroscopy in a wireless fashion. So that makes it the smallest magnetic field sensor that we know of. It's essentially just a single atom measuring the magnetic field. And with that, we can dream of experiments like this, where we attach one of these defects to the tip of a scanning probe microscope, we scan it across the surface, and we measure, for example, the magnetic field of single biomolecules. This has sparked dreams, and many experiments have been performed in many different approaches. So one, and they essentially can be distinguished in two classes. One is to use single nitrogen vacancy centers to perform experiments with moderate field sensitivity, nanotesla per root hertz. This is only barely better than the magnetic field sensor in the smartphone, in your smartphone. However, it's obtained by a sensor which consists of essentially a single atom. So it's a sensor which we can bring nanometers close to samples, for example, by embedding an ND center a few nanometers beneath the diamond surface and coating the surface with some material carrying a magnetic source, or by wrapping the NV defect in a nanodiamond, a little grain of diamond dust, and inserting this nanodiamond, for example, into a biological cell. It is also possible to use more than one NV defect, and in that way to average the signal to improve the sensitivity, obviously at the expense of spatial resolution, because the more NV centers they use, the larger the sensor will be. And theory predicts that by doing this at the micrometer scale, we can essentially go down to the picotesla per root hertz scale, and doing this on a millimeter size, large red diamond full of NV defects, we could even go to the femtotesla per root hertz scale. Many experiments have been performed. For example, this dream that I sketched a few slides earlier has become reality. People have really managed to make atomic force microscopy tips from diamond. This little brown piece of material is an AFM tip made from diamond. And at the apex of the tip, there is a single NV center in this diamond. And with that, leading labs in the field can obtain images of magnetic nanostructures, for example, of these stripe domains in a special kind of antiferromagnet. This has also been used to characterize the stray field of hard drive write-heads, for example, for a really close to industrial application. This technique has also been used for imaging, where again, we can implant ND centers close to the surface of a diamond, and we can implant them in large quantities so that we can no longer discern a single ND center. Essentially, such a densely doped diamond surface is a kind of smart cover slide that translates magnetic fields into fluorescence, and that we can image in a microscope. So a magnetic field on the surface of such an imaging sensor will affect the spectral lines of the underlying ND centers. These spectral lines we can turn into fluorescent, and by that we can image magnetic field. This has been used in particular by the laboratory of Ron Walsworth in formerly Harvard, now Maryland, to image magnetic inclusions in bacteria at the microscale. So this is a picture of magnetosomes, magnetic particles in bacteria imaged by ND centers. And this is a really popular application because this formerly could only be done by superconducting sensors. Now it can be done at room temperature in a usual biologist's microscope. One of my favorite applications is magnetic resonance spectroscopy. You may have been in such a device that takes a 3D image of your body by magnetic resonance tomography. Essentially, these devices produce a magnetic field map. This 3D image is essentially a map of the magnetic field, which is induced by magnetizing the patient in a strong magnetic field and polarizing the hydrogen spins in their body. The one Achilles heel of this technique has been spatial resolution. It is not possible to resolve details smaller than around a millimeter by traditional induction detection, and this is only a technical limitation. In fact, the signal itself does not scale with the size of the sample. If you could come nanometers close to a polarized section of tissue, the magnetic field that you would feel would be the same as at a millimeter distance of a millimeter-sized tissue. So if we had an atomically small sensor that could come nanometers close to molecules, then NMR spectroscopy could be extended to single molecules and much smaller entities. And this, in fact, has been successful. So a decade back, we have been able to use an ND center to measure the magnetic field of proton nuclear spins and adsorbents on the diamond surface. These are the first NMR spectra that we took. And that indeed means that we can use a single atom in a diamond 5 nanometers beneath the surface to perform NMR spectroscopy on such a few nanometers small volume, which essentially is comparable to a single biomolecule in size. Now, I would like to draw your attention to one thing. In the theory proposals that in a way started this field roughly 15 years ago, this was not the only vision that was put forward. So clearly, using a single NV to do NMR spectroscopy, all this was already part of the first theory proposals. However, there was on fairly equal footing a second vision that by integrating ND centers into large ensembles using densely doped diamonds, we would be able to achieve sensitivities that would be competitive with essentially superconducting magnetic field sensors as those that are being used for magnetoencephalography. And if that would be possible, that would be another very exciting direction for applications. Because, for example, it would be a competitive, cheaper room temperature alternative to do magnetoencephalography. It's fair, we have to be fair and say that there already is another quantum sensor that can do this. Optically pumped magnetometers, microfabricated vapor cells have now reached the sensitivity of superconducting devices and are increasingly replacing them in magnetoencephalography, so measuring magnetic signals of a living brain. However, they still have some drawbacks. They need to be heated. They are rather large. So it would be quite attractive if we could further compress this technology to an even smaller and even lower power device. And this is what NV diamonds could potentially do. Also, it could be possible to use spin sensors like nitrogen vacancy doped diamond as gyroscope for inertial navigation in autonomous driving, space navigation at JPL or wherever else. There also are interesting proposals going into a similar direction that simply by measuring the magnetic field very precisely and comparing it to a known map of the Earth's magnetic field, we could be able to do navigation in GPS-denied environments, which obviously is a very attractive task. However, if we look at the success stories of the past 2 decades, then it's quite striking that all these nanoscale dreams have pretty much become reality. We have seen atomic force microscopes using single NV centers as a smart magnetic field scanning probe. We have seen single molecule NMR being realized by NV centers. We have seen imaging at the microscale. We have even seen these experiments being performed in very exotic conditions like diamond anvil cells and enormous pressures. But scaling the sensitivity to levels that would be competitive with squids and vapor cells has not been as successful as these nanoscale sensors. So when we talk about the successes of quantum sensors today, these successes mostly capitalized on the fact that these sensors can be very small, not yet so much on the fact that these sensors can also be very sensitive. The best experiments that have been published have reached a sensitivity slightly below the picotesla scale. Now, that is a bit surprising. And even to only get to this level, a lot of effort was necessary. So typically, these best published experiments use a carefully prepared, very clean, but densely NV-doped red diamond, carefully engineered collection optics, parabolic collectors, complicated sequences with lock-in detection and other tricks to compensate for technical fluctuations of parameters like microwave power and so on. And with that, they routinely reach a picotesla per root hertz now, but this is still orders of magnitude short of the theory limit that in principle should be achievable. Also, if we compare that to the market of magnetic field sensors, a picotesla per root hertz actually is not that impressive by itself. For example, flux gates can also reach that. Induction coils can also reach that. They can even go slightly below a picotesla. It gets even worse when we look at chip scale devices. So these picotesla per root hertz setups are typically large lab scale devices. Once we move into compact integrated setups in a centimeter-sized physics package, that performance degrades to the nanotesla range. And if we reduce it even further to an integrated circuit style package, as has been done by the lab of Dick Englund at MIT, then that performance degrades to the microtesla per root hertz range. So clearly, one big dream of really having a competitive, sensitive magnetic field sensor that could go into an integrated circuit and possibly into a smartphone, that has not yet become reality. And I believe that part of this problem is related to the use of optical readout, because optical readout is technically quite some effort. It takes a laser for excitation. It takes complicated optics for detection, and it takes a lot of processing to account for systematic effects like drifts in laser power or drifts of background luminescence. Intriguingly, it turned out a few years ago that there could be another channel to actually directly connect NV centers to electric signals, and that is to use a connection in the microwave range. When we embed NV centers into a microwave cavity, we essentially can use them as a real circuit element. We can send a microwave signal through such a cavity, and this microwave signal can directly couple to the electronic ground state spin transition, because this is the spin transition in the microwave range. When we do this with a large ensemble, one can even reach the strong coupling regime, where the cavity resonance is split into a pair of cavity polaritons by coupling to the NV centers. And intriguingly, this can be used to implement readout of the spin state. For example, if we place ourselves in a region where the NV spins are fairly detuned from the microwave resonance, from the cavity resonance, if you look very carefully, this white line still does not fully coincide with the naked cavity resonance, which would be somewhere around here. So the presence of these NV spins slightly shifts the cavity resonance, and this can be seen as a change in the phase of a transmitted microwave signal. This can also be understood in a physical picture. The NV centers have a strong index of refraction in the microwave range due to the proximity to this ground state spin transition. So they effectively shorten or lengthen a microwave cavity, and they can imprint on a transmitted phase. And with this approach, it actually is possible to read out the state of the NV spins. At first sight, you might think that this should require a very narrow band resonator, and you might think that this would require a superconducting device, but in fact, it turns out that there are very narrow band resonators, even at room temperature, made from low loss perovskite ceramics, which can achieve quality factors like superconducting stripline devices in a room temperature device. So this is one of them. This is an NV diamond sitting in between. And this is something that we recently used in an experiment to read out the state of the NV centers. So have an NV doped ensemble sensor in a dielectric microwave resonator, excite this with a microwave antenna, and then repeatedly polarize and depolarize the NV centers to induce a spin signal. And indeed, we can read this from the microwave phase reflected from the resonator. Similar work has been done in the group of Dirk Englund, also achieving spin readout in such a device. Now, intriguingly, the performance of such a scheme could become rather good, because everything relies on a measurement of the phase of a microwave. And measuring the phase of a microwave signal is at the heart of everything in our modern life, from satellite navigation to cell phone communication. So it has been optimized to a great level of accuracy. In fact, you can buy phase detectors that can measure 9 digits of a microwave phase within 1 second. And plugging in these numbers into a theory calculation predicts that, in fact, with such a device, one might even be able to reach the limit of spin shot noise. This is one problem which I think is important to solve in our field, to actually integrate NV centers into real circuit and possibly also occupy this window of opportunity which has been so hard to reach in the past. I would also like to draw your attention to one thing here, which is this. Scanning probe microscopy with NV centers has been very successful, but the engineering effort required for this has been quite substantial. So it has been required to actually engineer AFM tips made from diamond. These can be done now, but this can only be done by a few groups in the world. And I think this is also a rather serious roadblock for our field. So we also decided to think about simpler engineering solutions for this problem. And we came up with a drastically simplified scheme, which is based on a somewhat bold idea, which is that it might be possible to also use an NV center in a rather large, tens of microns to millimeter sized planar bulk diamond. And it might be possible to bring this planar diamond nanometers close to a sample of interest if it was possible to align the sensor, the large bulk diamond, with the sample, and if the sample was perfectly flat. Indeed, it might be possible to actually take 2 millimeter large flat surfaces, and you could still squeeze them nanometers close together if you can align them sufficiently well with respect to each other. This sounds very daunting at first sight, but in fact, it is a rather well-mastered technology. Every hard drive essentially does this. In a hard drive, a magnetic field sensor made by lithography is flying nanometers close to an extended planar platter. Even in the 19th century, in optical machine shops, a similar technique was already used to bond optical surfaces in optical contact to each other. And so we did a little bit of research on how this could potentially be done. It turns out that ensuring this alignment is not a very difficult task. Ensuring it mechanically can be easily done by modern piezo positioners, and measuring the alignment to provide a feedback signal for positioning can also be done, for example, by using the sensor air sample dielectric interface as a Fabry-Perot resonator. You can observe Newton's fringes. So this is one of the sensors approaching to a planar surface, and we scan the height of this air gap between them, and we see dark fringes moving across the sensor every once in a while, which tells us that there is still some tilt between the sensor and the sample, and we can correct for this tilt and ensure perfect alignment. With this, we can actually do scanning probe microscopy in a very compact setup. So this is the setup that we use. It's roughly 10 centimeters in size. It operates with a commercial standard diamond, and it is a simple upgrade that you can add to essentially any microscope that is being used for NV centers. And we can now do this in an improved generation of devices, which you see here. So we use millimeter-sized diamonds. It turns out it's still advantageous to isolate a roughly 100 micron-sized platform on top of them. This looks a little bit like a tip, but it is a very blunt tip, and it is much easier to fabricate than the AFM tips made from diamond. Also, this blunt tip contains more than one NV center. So with the same sensor, we can have a choice of the number of NV centers that we use. And this is something that will be useful in that will be useful very soon. So we are now able to actually do scanning probe magnetometry with such a setup, where we essentially look at a single NV center, do spectroscopy of its ground state spin transition with some specific frequency. Then whenever we hit some specific line of the magnetic field where the ground state spin transition becomes resonant with this, we get these dark fringes. And from these dark fringes, we can infer a full magnetic field picture. And importantly, we can do this on the same sample using different NV centers in this platform. Each of these NV centers will give us a different projection of the magnetic field, so we can even do full vector magnetometry with a single sensor. With that, I'm at the end. quantum sensors have been a true success story in the past 2 decades. Nevertheless, there are still a few problems that I think we really need to work on. One of them certainly is readout. Optical readout is easy to implement, but it is remarkably inefficient. And if we really want to fill the remaining white spots, like, for example, very high sensitivity sensors, we need to find new ways. One very attractive route here, I think, is readout by microwaves and cavity QED. And we also need to democratize the technology, take it out from specialized lab, make it easier to access. And here, I think it's worth to think about alternatives to this very sophisticated microfabrication required for scanning probe experiments. I finally would like to thank the students that did the experiments that I presented today. Thank you for your attention, and I'm looking forward to your questions.
Thank you. Because we are a bit behind of the schedule, but we can have maybe 1 or 2 questions if anyone has questions. Any question? Okay. Okay, we can also look at the chat if there is something. Yes, go. Yes, please. Yes. Yes, go ahead.
It's basic, but I kind of catch how affect MRIs, like
How the crystal. How the crystal affects the MRI? Is that right?
Yeah. It's not my field.
It's not our field, but how does it affect?
How does it like?
What does it improve upon? Like, what is it detecting that an MRI is deficient in?
Farburg, maybe can you repeat the question? It somehow Zoom is cutting it off.
Sorry, we don't have a microphone, unfortunately, in this room. If you don't mind, and I'm not sure if you move this again, it may stop. If you like to ask here, go ahead, please.
Hi, just my question was, how does quantum crystals improve the MRI? Like,
Oh, yes.
that, yeah,
Yeah.
okay, thank you.
Yeah, well, now it was crystal clear, the audio. Thanks a lot. Well, I think it's important to note, this is a question I often get from general audiences, for example, that it's not easy to see how it would improve clinical MRI, right? So NV centers, the strength of NV centers is making MRI possible on very small volumes, on microscale objects or even on nanoscale objects. It's not easy to see a clinical use case because you would have to freeze a patient and slice them into pieces to make them amenable to diamond sensors. So this is obviously not quite realistic. However, they really open a new window of opportunity when it is about MRI of microscale and nanoscale samples. And here you could, for example, think of doing single cell studies, doing metabolomics on single cells, or doing studies on the nanoscale, looking at single biomolecules, possibly imaging them in 3D by MRI, or if that's not possible, maybe at least looking into their dynamics, diffusion properties on abrasive films. For example, when you slide something on the diamond surface, really looking at the tiny lubricating layer below it by NMR and MRI. These are visions that we have for the future.
Extremely interesting, because I'm assuming you can do all of that live and get better resolution.
Can you do that to get better resolution?
Well, yes. So the resolution is way beyond what you can achieve with induction detection. Whenever the sample is smaller than, I mean, say around 100 microns, clearly NV centers are better than what can be done by shrinking the existing MRI and NMR technology.
think the question was actually like, can you do it live?
Can you do it live?
Yes, it's all operating under ambient conditions, and even under exotic non-ambient conditions. So you can do it at room temperature in a liquid. You can even do it in a heated oven. If you want to look at high temperatures, you can do it in a diamond anvil cell at high pressure. You can also do it at cryogenic temperatures, but you don't need to do it. It can be ambient.
Thank you very much. Okay, thank you again, Dr. Professor. Thank you. Great presentation.